So far this semester, we've focused our attention primarily on the CPU. We've talked about the circuits that make up the ALU, the registers, and the control unit. And we've thought about how our programs in a high-level language like C get translated into assembly instructions that control the operations that the CPU performs. Up to this point, our discussion of memory has been almost entirely abstract. We've been thinking of RAM as though it were a great big array where we could put data at any location in that array by specifying an address. When we're writing programs, this is often the right level of abstraction at which to be thinking about memory. But sometimes it can help to pick apart that abstraction and think about what's going on underneath. And so today, and in the next few lectures, we're going to be thinking about some of the things that are going on under the hood when we transfer data to and from memory. To talk about memory, the first thing that we need to get a handle on is what sorts of instructions send data to memory and what sorts of instructions retrieve data from memory. When we're retrieving data from memory into the CPU, we call that a read operation. And when we're sending data from the CPU into memory, we call that a write operation. So for some of the assembly instructions that we're familiar with, we can think about when are they reading or writing data. If we begin with this move operation, we have a source and a destination. Here, the destination is a register, so the place that we will eventually be putting data is the EAX register. And as we know, the registers live inside the CPU. But the source for this operation is a memory address, which we can recognize by the parentheses in the assembly instruction. So we'll be taking the address in the base pointer register, adding 8 to it, and retrieving data from that location in memory. To carry out this operation, the CPU has to perform the arithmetic to figure out what address is it requesting data from, and once it has calculated that address, it will send on the wires that connect the CPU to the RAM the address of the data that it's looking for and an indication that it wants to read from that address. The wires that go between different components in the system are typically referred to as a bus. In response to the read request from the CPU, the RAM will locate the data and send it back to the CPU over that same bus. And the end result is that we will have moved the number 3 from a location in RAM into the register EAX. So this was a read operation. We brought data from memory into a CPU register. Our next instruction here is performing an add, and the add takes data from 2 different locations and sends those to the ALU to perform arithmetic. One of the locations we're getting the data is from memory, again indicated by the parentheses. The other location we're getting data is from the EAX register. So the CPU will first compute the address that it needs to send on the bus and request from RAM the data at this location. At that location we have the number 8, and so that will be sent back to the CPU and given as an input to the ALU. And the other input to the ALU will come from the EAX register, at which point the ALU will perform the addition, getting the result 11, and storing that into the destination, which in this case was the EAX register. And so we end up with the value 11 in EAX. And so once again, this instruction performed a read operation, since it had to retrieve data from memory, and it did not perform a write operation because we didn't have to send the result to memory. The result went in a register, which lives inside the CPU. If our next instruction is to push the value in EAX onto the stack, then we are taking this value and putting it on top of the stack. When we do that, we subtract 4 from the stack pointer, and then we store the data at that location in memory. To do this, the CPU will need to send over the bus first the address where it wants to put the data and an indication that it wants to write to that location, and then it will send over the bus the actual data being written. And the end result will be that at this location in our address space, we will store the value 11. So in this case, the source for our data was a CPU register, so we didn't have to do a memory read, but the place where we put the data was in memory, and so we did perform a memory write. Each instruction in our assembly program can potentially perform a read, a write, or both, or neither. Now that we have a sense of read operations that retrieve data from memory, and write operations that send data to memory, we can actually start to think about how do these interactions with memory happen under the hood. And the first thing we might want to think about is the addresses that we've seen in our assembly programs. If we're thinking about RAM as a great big array of bytes where our programs can send data to or get data from any address, that would imply that our program has access to the whole range of addresses expressible as 32-bit unsigned integers. If we translate this hex address into decimal, it represents the number 4,294,956,160. And it might seem silly that our program is accessing data at address 4 billion and something, implying that it has access to over 4 gigabytes of RAM. And this would be even more ridiculous in 64-bit assembly, where we might see addresses in the quadrillions. So clearly, these addresses that our program refers to don't actually constitute indices into the data on the RAM chip. There clearly must be some sort of translation going on. Another reason we know there must be some translation going on is that if we run several different programs at the same time, those programs could all be referring to the same address, but they would not be reading and writing one another's data. Different programs have separate address spaces, and so it must not be the case that each program is accessing data at this literal index of the RAM. So what's going on here is that under the hood, the operating system is translating the addresses that our program is thinking about, which are known as virtual addresses, into physical addresses that actually get sent to the RAM to retrieve or store data. There is some hardware inside the CPU that assists with this translation process, and the operating system gets to decide which portions of the physical RAM are allocated to different programs running on the computer. And so when your program requests data at a particular virtual address, that will get translated by a cooperation between the operating system and the address translation circuitry into a physical address that is actually sent to the RAM in order to retrieve the data. This address translation process ties in with decisions that the operating system is making about how much memory gets allocated to different programs. And we will talk in depth in a future lecture about how the operating system manages the mapping between your program's view of data and where the data is actually stored in the RAM. Another way that the abstraction we have been using to think about memory is inaccurate is that there are actually many different types of memory within a typical computer. In addition to main memory that lives on RAM sticks, there's also memory that lives physically inside of the CPU. This memory is known as cache, and it actually takes up a physically large fraction of the space inside of most modern CPUs. This cache memory is much faster to access than RAM, but is also much more expensive to manufacture, and therefore is smaller in capacity. The job of the cache is to store a subset of the data that's in RAM, so that when your program issues, for example, a read instruction, some of the time it will be the case that the data you're looking for is already inside the CPU and can be accessed much quicker. If the data that we're looking for is already in the cache, then moving it to a register can be done entirely within the CPU, avoiding the need to send signals to the RAM and wait for the response, which speeds up the execution of that instruction significantly. The cache and the RAM are both parts of what we more broadly call the memory hierarchy. The memory hierarchy is based on the idea that different ways of storing data differ in terms of speed, cost, and capacity. At the top of the memory hierarchy are the smallest, fastest, most expensive ways of storing data. And as we move down the hierarchy, we get larger capacities and cheaper cost, but slower access times. The fastest storage to access is the CPU registers. And in general, if the operation that the CPU is performing relies only on data that's already in registers, that operation can be completed in a single clock cycle. But as we go down the memory hierarchy, each subsequent level involves at least an order of magnitude slowdown in the access time. For example, accessing data in the fastest level of cache typically takes around 10 clock cycles. It's actually common for the cache memory inside a CPU to have multiple distinct levels, where those levels are separated by speed and capacity. So there will be a small, very fast level 1 cache, then a larger, slightly slower level 2 cache, and the largest and slowest level 3 cache, which is still much faster than accessing the RAM. As we go down subsequent levels of the memory hierarchy, we again have significant slowdowns in access time. And beyond RAM, we can think of the computer's hard drive as a type of storage that is higher capacity than the RAM, but also much slower to access. Hard drives also have the feature that they are persistent storage, meaning you can turn the computer off and not lose the data. But in fact, when we talk about virtual memory, we will see that one of the decisions that the operating system can make is, if the RAM is too full, it can send some of the data that should be in RAM to the hard drive temporarily and retrieve it back into RAM the next time that it's needed. And we could even think of data that would be retrieved from an external drive or from over a network as being part of the memory hierarchy, where sources of data external to the computer are even larger capacity, but also even slower to access than the hard drive. But I've separated out here the three levels of cache and RAM and disk as the main levels that we will be thinking about when we talk about memory operations. When we think about read or write operations, we're thinking about, is data being sent outside of just the registers? If we have to send data to the cache or to the RAM or to the disk, then we're performing a write operation. Whereas if the data stays only in the registers, that's much faster and is not a thing that we have to analyze as a memory operation. So even though registers fit within this hierarchical model, we will think of them separately from the levels that we're talking about as memory. And I've also separated external storage because we are not going to focus on it in this class. So over the next few lectures, we will need to think about how do decisions get made about what data is stored in what level of the memory hierarchy. As I mentioned, the data in the cache is generally a subset of the data in the RAM. And in fact, when there are multiple levels within the cache, it is typically implemented such that each smaller level contains a subset of the data at the next level down. The reason for this is to provide exactly the abstraction that we have been thinking about so far. If you write assembly code and want to read data from memory, you as the programmer are not obligated to think about, is the data in the level 1 cache or the level 2 cache or RAM or what? By ensuring that each level is always a subset of the next, we can make it so that the programmer only has to ask for data by address, and that address can be sent to each of the levels in turn to see if the data is there. And the first one that gives back the data that we're looking for will allow the operation to proceed. So the decision about what data to put where then boils down to which subset of the data should be kept in the smaller, faster level that's higher in the memory hierarchy. These decisions are made collaboratively by the operating system and the hardware, and the goal in making the decision of what subset of data to include is to ensure that most of the time the data we're looking for is in the highest possible level of the hierarchy. So to figure out how should we decide what data goes in the smaller, faster levels of the hierarchy, we need to think about how we can make predictions of what data is likely to be needed by a program. If we could predict the future and know in advance what data a program was going to operate on, then we could ensure that it is always in the background being brought into higher levels of the hierarchy so that when the program tries to access data, it's always available as quickly as possible. But since we can't actually predict the future, we have to instead rely on some heuristics. The first heuristic has to do with the fact that the code of our program, as we know, lives in memory, and for every operation being performed, we need to fetch and decode that instruction before we can execute it. And if we think about the execution of a typical assembly program, most of the time the program proceeds from one instruction to the next. That means that if we are currently executing this instruction, it is pretty likely that the next instruction we will execute will be the one that immediately follows it in the assembly program and therefore in the code segment of memory. And so the system can speed up the average fetch time for assembly instructions by ensuring that the next few instructions of the assembly program are always being brought into the highest level of the cache. But we'd also like to ensure that the accesses to our program's data memory in the stack and heap segments are efficient whenever possible. So we can develop other heuristics for predicting what data our programs are likely to access in the future. And those heuristics are based on ideas of spatial and temporal locality. Spatial locality is the idea that data that is near other data that we have recently accessed is likely to be accessed soon. This is common because many programs that we write will, for example, iterate through an array. In this C code, we are looping through the characters of a string and capitalizing them. And so if we have just executed iteration 0 of this loop, iteration 1 is going to access the next element of the array. And as we know, elements of an array are stored at consecutive memory addresses. So when our programs access multiple things in memory that are near one another, that's known as spatial locality. And what spatial locality implies is that we can often speed up access times by bringing in a block of nearby data to the cache, because if we accessed one element of our address space, there is a good chance that we will soon access other data that is nearby. And so if on the first access a block of data is brought into the cache, then the subsequent accesses will find the data that they're looking for in the cache and be able to execute faster. Another beneficial heuristic is based on the idea of temporal locality. Temporal locality says that if a program has accessed a particular memory location recently, there's a good chance that it will access that exact same location again soon. Temporal locality happens because we often refer to the same variable over and over again. For example, in the C code for computing Fibonacci numbers, our loop accesses the same few variables on every iteration. And so this means that if data was recently brought into the cache or recently accessed while in the cache, it's a good idea to keep it there because there's a good chance that it will be accessed again soon. So these ideas of spatial and temporal locality will inform the heuristics that the operating system and the hardware will use to decide which things get kept in higher levels of the memory hierarchy. And because heuristics based on spatial and temporal locality are being used, that means that as a programmer, we can often make our code execute more efficiently by increasing its spatial or temporal locality. If our code issues a read or write instruction, and the data that we're looking for is already in the cache, that's known as a cache hit. And a cache hit means that the instruction will complete much more quickly than in the case of a cache miss, where the data we're looking for is not in the cache and we have to go retrieve it from memory. So we can increase our cache hit rate by writing code that conforms to spatial and temporal locality. Specifically, a way that the system takes advantage of spatial locality is by moving around blocks of data. When data is transferred from the disk into RAM or from RAM into cache, a block of adjacent addresses are all sent at once. So if we access the first element of our array, that will be brought into the cache, and along with it will be brought several other nearby pieces of data. And so if we access the elements of our array in order, it's likely that subsequent accesses will often be cache hits because the data that we're looking for was brought in on an earlier operation. Whereas if we were to jump around our array at random or by big steps, then it's less likely that the data that we're looking for will already be in the cache. This video has given us our first peek underneath the abstraction that we've been using so far to think about memory. We'll come back to ideas like address translation and deciding what data goes in the cache in future lectures, but I hope you've come away with an idea of what read and write operations look like, how locality can appear in our code, and how the memory hierarchy as a whole can have a big effect on the efficiency of our program.